Bismillah ar-Rahman ar-Rahim. Alhamdulillah wa salatu wassalam ala Rasulillah amma ba'd. This lab deals with pulse width modulation. Pulse width modulation is a technique to change the duration of pulses to vary output voltage. So in this example shown here on the screen, you have periodic pulses with different width for the on signal. So in PWM, by varying the width of on pulse and off pulse, we can vary output voltages. Another example shown here. A normal DC supply has 100% duty cycle, so it can only change from 0 to 5 volt. So once the DC supply is switched on, a 5 volt DC supply is switched on, it stays constant all the time. So you have 5 volt as output. The average output voltage will be 5 volt. Now in this example, we change the duty cycle to 75%. So for this periodic signal, for 75% of the time, the pulse is on and 25% is off. So the output voltage here, the average output voltage generated here at the load will be 3.75 volt. Now in this example, you have 50% duty cycle. For half of the time, the pulse is on, and for half of the time, the pulse is off. So the output voltage will be 2.5 volt. And in this example, you have 25% duty cycle, and here you have 0 duty cycle. So 0 duty cycle, that means the signal is off completely. Now in PWM signal, you have two parameters. You have the frequency of the pulse, which depends on the period of the periodic pulse, periodic signal, and you have the duty cycle. The duty cycle is defined as on time divided by the complete period of the signal. In PIC microcontrollers, there is a module known as capture, compare, and PWM module, CCP module, capture, compare, and PWM module. This module works in 3 different modes. It has capture mode, compare mode, and PWM mode. In this lab, we study the PWM mode of this CCP module. So in PWM mode, we use this register, CCP1 control register, and we use another register known as PR2 register, and another register known as CCP1L register. So this figure shows you the output of a PWM signal. So you have the duty cycle, which is on time divided by the complete period of the signal, and PWM period is calculated using this equation. So PR2 is name of a register, PWM period, so period is the reciprocal of frequency. So whatever period you need, you can substitute the period here, and PR2 is name of the register. So PR2 plus 1 multiplied with 4 multiplied with time of oscillative frequency. So again, TOSC is 1 over FOSC, oscillator frequency, multiplied with timer 2 prescaler. PWM, to generate PWM signals, PIC microcontroller, it needs timer 2. Timer 2 must be switched on, and timer 2 must be running in the background. So PWM, the CCP module, takes help of timer 2 to generate the timing signals for the PWM signal. So the timer 2 prescaler, by default it is 1. If you don't change it, keep the value as 1 in the equation. TOSC is 1 over FOSC. So if you have 4 megahertz as the oscillator frequency, this will be 1 divided by 4 mega. And PR2 is the unknown. So calculate the unknown value depending on PWM period. you have to define the period. So calculate this unknown value and copy that result in PR2 register. So this will define the period of the PWM signal. The PWM duty cycle. The duty cycle bits are stored in these two registers, CCP R1L register and 2 bits, bit number 5 and 4 of CCP1 control register. The PWM duty cycle in PIC microcontrollers has 10-bit resolution. The 8 bits, the higher 8 bits are in this register, CCP R1L register, and the lower 2 bits, they are in the CCP1 control register. So these two bits of CCP1 control register, these are the two LSBs of the 10-bit duty cycle. So you have 10-bit duty cycle for generating, for calculating the duty cycle of PWM signals. The higher 8 bits are in CCP R1L register, and the lower 2 bits are these 2 bits in CCP1 control register. These are the lower LSBs. Now, the CCP1 control register has the mode selection bits for selecting capture mode, compare mode, or PWM mode. So these 4 bits, the lower 4 bits of CCP1 control register, they are used to select capture mode or compare mode or the PWM mode. So for PWM mode, the bit values are 1100. Now in PIC microcontroller, where is the output generated? The output signal or the CCP, the pulse width modulated signal, where is it generated? It is generated on CCP pin of microcontroller. The normal CCP module, the PWM signal is generated on this pin of microcontroller, CCP1 pin. Some of the microcontrollers, they have multiple CCP modules. So in PIC18 4580, we have a single module. So it is generated on CCP1 pin number 17 of the microcontroller. Now this was the CCP module, CCP1 control register, the normal CCP module. In few microcontrollers, in some of the microcontrollers like Pwm 18F4580, we have the enhanced version of CCP module as well. In the enhanced version, these are the 2 extra bits which were not there in the normal version. So if you look at this version, section 15, these 2 bits are not used, they are blank. But in the enhanced version, these 2 bits are also used. Now, what is the application of pulse width modulation? Pulse width modulation can be used as a dimmer for LED lamps, or they can also be used to control the speed of a DC motor. So it can be used anywhere in an application where we can supply analog voltage as input. If you apply a filter on PWM signal, we can get an output, an analog output in this way after applying an RC filter. So this analog signal can be used to control the speed of a motor, or it can also be used to control the output voltage for any application. In our application, we are using the CCP module to control the speed of the DC motor on the mechatronics demo board. So in the mechatronic demo board, the DC motor is connected in an H-bridge format in this way. So this type of connection is known as a full bridge connection or an H-bridge connection. Here, in this case, the motor can be controlled in both the directions, forward and reverse. The example is shown here. In the full bridge forward connection, this MOSFET is switched on, and this MOSFET is fed with a PWM signal. And the other two MOSFETs, they are switched off. So the current flows in this direction, and the motor rotates in clockwise direction, for example. And the speed of the motor is controlled by switching this MOSFET on and off using a PWM signal. So by varying the duty cycle, you can either increase the speed of the motor or decrease the speed of the motor. Now in the reverse format, these two MOSFETs, they are switched off. This MOSFET is switched on, and a PWM signal is sent to this MOSFET. So in this way, the motor rotates in the other direction, and you can control the speed of the motor by changing the PWM signal, duty cycle of the PWM signal on this MOSFET. Now for a full bridge connection, we need 4 outputs, 4 connections. So for 4 connections, the microcontroller in the enhanced version, it uses all these pins of the microcontroller: P1A, P1B, P1C, and P1D. If you look at the pin diagram, we find these pins connected here: P1A, P1B, P1C, and P1D. So these are the pins on which should be connected in a full bridge connection. So in the normal CCP module, in this module, the pulse width modulated signal is generated on this pin number 17, CCP1 pin of microcontroller. But in the enhanced version, the PWM signal is generated on all these 4 pins of the microcontroller, and we can control that using the extra 2 bits in the enhanced version. Now let's look at the CCP1 control register again for the enhanced version. So in this version, Pwm mode has 4 options. In one, if we select 1100, P1A, P1C are active high, and P1B and P1D are active high. Active high means it uses positive logic. So in positive logic, high is 1, 1 is 5 volt, and low is 0 volt. But in the other case, here we have 1101. In this case, P1A and P1C are active high, and P1B and P1D are active low. So in the active low case, the logic is opposite, it's the negative logic. So if the active output will be 0 and the inactive output will be 1. So that depends on, the selection depends on the type of MOSFETs used in the connection. So you have P type of MOSFETs. So P1 and P2 are the P type of MOSFETs, and N1 and N2 are N type of MOSFETs. So here we have P channel and here you have N channel. So the control circuit for P MOSFETs and N MOSFET is entirely different. And as you can see, the buffer connected here, it has a NOT connected here, and this buffer does not have a NOT. Okay, so these are simplified circuits. So if you want to switch on a P MOSFET, then you should send a 0 on the gate. But if you want to switch on an N MOSFET, then you should send a 1 on the gate. Since we have this buffer circuitry already connected here for the N and P MOSFETs, we do not have to change the logic of the output pins. So we can simply use active high logic for all the 4 pins of PWM signal. So in this case, we will choose 1100 for the PWM mode with all of these as active high. So this is the mode selection, and PWM mode is selected using CCP1 control register. Now the next part is, before coming to the remaining bits, the next part is configuring the period or the frequency of the PWM signal. So as we have seen in the data sheet, the period of PWM signal is calculated using this equation: period equal PR2 plus 1 multiplied with 4 multiplied with TOSC multiplied with time to prescaler. So PR2 is the unknown, period is the calculated value, and TOSC is 1 divided by FOSC, and time to prescaler by default it is 1. So calculate the given period and load that value in PR2 register. The PR2 register, if you rearrange the equation, we can write it in this format. So PR2 equal period divided by 4 multiplied with TOSC. The TOSC can also be written here in the numerator. So FOSC multiplied with period divided by 4 and divided by the time to prescaler minus 1. So this will give you the frequency of the PWM signal. And the next part is the duty cycle. For duty cycle, we use both these registers, ECCP R1L register. So this will hold the higher weight bits of the duty cycle, and the lower two bits, they are in bit number 5 and 4 of ECCP1 control register. Now going back to the control, PWM control register once again, bit number 6 and 7, they are only used in the enhanced version, and they can be used to control the direction of rotation of the motor. So if these two bits, if these are 0 and 0, then we have a single output. If these two bits, then the extra two bits here in the enhanced version, if these two bits, they are 0, 0, we have a single output, and that output will be on P1A pin of the microcontroller. P1A pin of the microcontroller, which is this pin, and this pin also shows you ECCP1 as the output. So if those two bits are 0, 0, you have a single output on this pin. The PWM output signal is generated on this pin. Now if these two bits are 0, 1, then P1D is modulated, which means the PWM signal is generated on P1D and P1A is active. That means P1A will be on, B and C will be inactive. So the configuration now looks like this. It looks like this. P1D, this is modulated. That means the PWM signal is generated on P1D and P1A is active, and B and C, both of these, they are off, they are inactive. So this is the full bridge forward output. Then in the full bridge reverse output, you have P1B modulated. So PWM signal will be generated on P1B and P1C is active, A and D are inactive. So once again, B is modulated. So the PWM signal generated on P1B, and this pin P1C is active, which is on all the time, and A and D, they are switched off, they are inactive. In some applications, we don't have a full bridge connection. We only need a half bridge connection. So in half bridge connection, we can control the motor with only 2 MOSFETs. So this option here is for a half bridge connection. So this is a half bridge connection which has only 2 MOSFETs connected, and you can control the motor here in this way. And half bridge connection can also be connected in this way as well. So even in this way, the motor can be controlled in both the directions by sending a PWM signal either on these 2 pins or on these 2 pins. This is the full bridge connection, P1A, B, C, D, full bridge mode. And This is one type of half bridge connection. Full bridge connection. This is the half bridge connection. So if you want to use the motor in half bridge connection, then you can use this mode 1-0. So in 1-0, A and B will be modulated, and P1C and D will be assigned as port pins. So you can use them as input or output ports. So in our case, if you want to switch the motor between forward and reverse, we have 0, 1 and 1, 1. So by simply toggling bit number 7, of ECCP1 control register, you can switch the direction of the motor between forward and reverse, and you can keep bit number 6 as 1. And the last 4 bits will be 1, 1, 0, 0. The remaining 2 bits here for the duty cycle will depend on the duty cycle that you select. Now in the activity, we have this motor connected on P1, A, B, C, and D. And the feedback of the motor is connected on timer 1 clock pin. And there is a button connected on update 0. And there is a potentiometer. This is a potentiometer connected on in2 pin. So in the activity, you have to get analog input from in2 pin from the potentiometer and use the ADC result to control the duty cycle of the motor. So that will control the speed of the motor. So as you increase the potentiometer, the speed of the motor will increase. And if you decrease the potentiometer, the duty cycle will decrease and the speed of the motor will decrease. So control, get analog input from potentiometer on in2. You have 10-bit ADC result. You can use those 10 bits directly as the duty cycle for the DC motor. Or if you want to make your program simpler, you can use higher 8 bits of the ADC result. Use only higher 8 bits of ADC result and copy them to the higher 8 bits of the duty cycle, which is ECCP R1L register. So copy those higher 8 bits of ADC result in this register. So that will set the duty cycle, and you can keep the remaining 2 bits, the lower 2 bit LSBs of duty cycle. You can keep them zeros if you want, or you can keep them ones. It does not matter. You can keep the lower 2 bits as 1. So this will control the speed of the motor. Now to control the direction of the motor, use this button. When this button is pressed, simply toggle bit number 7 of ECCP1 control register. So if you toggle this bit number 7, the direction of the motor changes from full bridge forward to full bridge reverse. So depending on the button, simply toggle that bit and that will change the direction of the motor. And you get a feedback on timer 1 control register. So timer 0 can keep track of time. Use timer 0 to generate an interrupt on every 600 millisecond. So every 600 millisecond, get the reading from timer 1 registers and display them on the LCD as the RPM of the motor. And timer 2 must be switched on before switching on PWM. Timer 2 must be switched on, and do not change the prescaling timer 2, keep it 1. So timer 2 will help the PWM to generate the timing signals. These are the steps for the activity. Configure ECCP module to generate a PWM signal. Read ADC input from potentiometer. Use ADC result to control the PWM duty cycle. Use PWM signal to vary the speed of the motor, and use the push button to control the direction of the rotation of the motor. Configure timer 1 to use optical interrupter, which was the feedback from the DC motor on mechatronic demo board, and timer 0 to generate interrupts every 600 milliseconds. So on every interrupt, read timer 1 value on every interrupt and display the RPM divided by 100 on the LCD. This is the template for writing your program. In the interrupt function, check the timer 0 interrupt flag bit, clear the flag bit and copy the value of timer 1 registers in a variable RPM. RPM is defined as an unsigned integer here. And clear timer 1 registers for the next cycle or for the next count, and reload timer 0 registers with the initial value that you need to generate an interrupt on every 600 milliseconds. This is another function, a user-defined function, set motor speed. So in this function, we set go bit to start ADC conversion. Once the conversion is completed, copy ADC result to ECCP R1L register. So you are copying only the higher rate bits here, and then display the ADC result on first line of LCD, and this can be displayed on the second line of LCD. Displaying the RPM is done inside the main function. So configure oscillator control for 8 MHz frequency of internal oscillator. AD control 1 register to configure all pins in the digital format except in2 in 0. Potentiometer is input, PWM is output, push button is again an input, timer 1 clock pin is input. Configure AD control 2 for left justified, 40 AD FRC clock, and configure AD control 0 for into channel, and configure PR2 for 19.61 kHz frequency, and configure ECCP1 control register for PWM mode with all active high output. Use timer 2 on bit from T2 control register to switch on timer 2. Then configure the LCD port as an output port. Initialize LCD. So these are the functions from the LCD header file. Configure timer 0 to generate interrupt on 600 milliseconds. Use a suitable scaler. Calculate the values that you need. T0 control register, timer 0 high byte, timer 0 low byte. These same values, we'll have to reload them in the interrupt function again. Timer 1 counts external pulses on timer 1 clock pin with 1:2 place scaler, because we have 2 slots in the disk on the DC motor on the mechatronic demo board in the lab. And timer 1 control register, load the value here. Display RPM by 100. You can display it on the second line of LCD, because on the first line you are already displaying the ADC result. The first line of LCD is displaying the ADC result. So here you can display this on the second line of LCD. RPM divided by 100. You can display it on the second line of LCD. And in front of that, you can display the actual number. So clear timer 0 interrupt flag, enable these interrupts. Now in this case, by default it is forward mode, and check input from the button. Whenever the button is pressed, you have to simply toggle bit number 7, which is this bit. You simply have to toggle this bit of ECCP1 control register. So when this bit is toggled, the direction of the motor will change. Set motor speed function, the user-defined function. You are calling the function and displaying RPM on the LCD. So you can display it on the second line. After you display this, you can display it in front of that. And this is a simple delay here. So use X8 compiler to compile the program and test the working in the simulation in Proteus. So this is all for this lab. Complete the lab, and for more details, you can go through this link. You can read this chapter. You can read the explanation given here for using the CCP module. This chapter is based on PIC18 microcontrollers, but most of the concepts are same. You will find small differences in bit names in different registers. So complete this activity, and you can submit it online on Blackboard. Assalamu alaikum wa rahmatullahi wa barakatuh.